Hello, I'm Roy Ruddle, and this video shows you the second step of the 6-step data quality method. I've been working in data quality for more than 10 years, and we developed the method with input from data scientists and analysts working in more than 15 industry domains. The method is freely available, and you can download it from this GitHub link. We have designed the 6-step method to let you investigate the quality of your data efficiently, rigorously, and reproducibly. There are 3 types of benefit, and these are enabling you to do more in less time because the method tells you what to do, reducing cost because we have grouped data quality checks into a carefully thought out order, and letting you get better results because by following our method, you will understand the limitations of your data, correct misheld assumptions, and be able to clean your data as you progress through the 6 steps. We have created 7 videos, an overview as well as a different video for each step. Step 2 is about special values, and this video walks you through it in a worked example. Special values sometimes occur by accident because of system defaults. More often, special values are a sign of good quality data that has been processed to flag values that were missing, unknown, or invalid. I'm going to show you 5 ways to detect special values. First, I'm going to look at a case where the dataset is well documented. Then I'm going to show you 4 approaches that help when the dataset is undocumented. I will use a different dataset for each approach, and as I've already said, the method is freely available. You can use any software to perform the 6-step data quality method. However, the examples I'm using in the videos use Python, the Viz Data Quality package, and Jupyter Notebooks. So here is the Jupyter Notebook that I'm going to use, starting with the approach for when the dataset is documented. The first thing to check in a dataset is whether it has documentation, and especially if it's machine readable. If it is, don't ignore it. Treat it as the most precious data of all, because good documentation is gold dust. That's exactly what we have in this road safety data that I'm showing you here. Okay, so here is the documentation for the road safety dataset. It's an Excel spreadsheet. You can see that there are a number of tables in the dataset. The tables have a number of fields or variables. Some of those fields can have multiple values. For example, police force could be 1, 3, 4, 5, and so forth. And these are lookup table values where the label column is telling us what each of those integers stands for. If we scroll down in this Excel spreadsheet, then you'll notice things like values indicating data was missing or out of range, or a value was unknown. And we're going to make use of these labels to automatically detect the special values in our dataset. So to analyze this, I'm going to load the documentation just like a dataset, and then I'm going to search in the label column for any value that contains the word missing. Now the word missing appears in quite a lot of rows of that dataset, but they all say exactly the same thing, the same label, which is data that is missing or out of range. I can do the same thing for the word unknown. And here I find a variety of different values that appear in the labels. Having found those, what I would do is to flag all of these values as nulls and then to proceed with the analysis. Now let's move on to the 4 approaches to use if your data is not particularly well documented. The first of those are special values that are widely used. So data science software like Pandas tries to make your life easy, and I bet that if you use Pandas, you've also used the read CSV function to load in text files. And what Pandas does for you conveniently by default is to change blank cells that contain text like NaN, Na, or null into missing values. And this sounds very good, but what do they mean by it also does that for other common representations of missing data? To investigate that, I'm going to load the dataset twice. I'm first of all going to load it so that only empty cells are treated as missing, and then I'm going to load it into a separate data frame, making use of the Pandas defaults, and then I'm going to use a convenience function from visDataQuality to find the difference between those. So what you find if you do that with this particular dataset is any text that is the word none is treated as a missing value. And I'll point out that none is not one of the three named values that are up here, so none must be one of the other so-called common representations of missing data. Now let's ask ourselves, what similar values did Pandas leave unchanged? So now I'm going to loop through the data frame that use the defaults and look for any text that contains the word none. You find that there are in fact three other versions of the word none. There's none that's entirely lowercase, none that's entirely uppercase, and none that's got a capital N and an O. And these appear in 4 different variables, but none of these have actually been treated as missing values. So there's a great inconsistency here between the word none with a capital N and the word none with any other capitalization. There are 2 take-home messages from this. One is, it is always dangerous to use defaults blindly. Check it. The second one, as I'll show you in a moment, is that the word none is actually a valid value in these particular fields. So here is the bus stop dataset. I'm going to focus on the shelter type column, and you can see in that various values, including the value none, indicating that there is no shelter at that particular bus stop. And if we scroll down, we can see that some of the cells are genuinely missing, as opposed to having the word none indicating there's no shelter. Let's go on to the next approach, is where you have text values in a numerical column. This example is using a data set about leakage from water supplies. And when we read the data in, we find there are a load of year-month columns containing the leakage readings. These are numerical, as we'd expect. But what takes us by surprise is that latitude and longitude are not numerical. They have a data type of being an object. So we need to investigate that. What we can do is to use a convenience function in visDataQuality to find the non-numerical values of latitude and longitude. And when we print them out, we find that there are 2. #NA is what's used to indicate that the value is missing. When the values are missing in the year-month columns, the cell is left empty rather than using #NA. But what on earth is this top-end additions? So here we're looking at the data set. You can see these columns here are month and year, and they have the readings for the amount of leakage at a given place. And we're interested in these 2 columns, latitude and longitude, because they're the ones that had textual values in columns that should and appear to be mostly numerical. We scroll down through this. We'd have to keep going for quite some time, but you'll see that there are some examples here of #NA to indicate that the latitude and longitude were not known. And if we scroll to the bottom of the file, this is where we find that strange term top-end additions. And now that we can see that in context, we can see that actually the very last row in this data file is a summary row. And so by detecting these textual special values, it's led us to realize that we need to make sure we do not include this last row when we load the dataset. Otherwise, all of the numerical data that we're getting down here is going to be massively skewed. The next approach is where large positive or negative integers or very old dates are used to have a special meaning. Now, this example is not open data. It comes from a very large hospital data set, which I've processed to extract the unique values for 3 particular variables. The first of those variables is the admission age of the patient. If you plot the unique values, you see that most of the ages are in the range of roughly 0 to 100 and something, but then there was one very large value. And actually, in this case, if you look at the data dictionary, it is a well-documented data set. It will confirm that the value 999 is used where the patient's age was not known. So you can see how well this stands out. However, with the 2 other variables, episode order and a lookup table for the admission source, there are no outliers that stand out, and that is because the valid values are in the range of 29 to 89 and 1 to 87, whereas the special values, again documented in the data dictionary, are numerically not very different from those valid values. In other words, this approach of plotting a box plot and looking for outliers of the unique values of a variable is not foolproof, but it can be very useful if you're dealing with data which is not well documented. Now we'll go on to the last of the examples, and this is to do with default values, and for this I'm using a dataset about water meter readings. Once again, I load the dataset into a data frame. I calculate some statistics, and then I'm doing a stack bar chart of all of the variables here, showing the number of values that are present in blue, the number of missing values in green, and the number of zeros. So we can see that 2 of the variables are complete. The rest of them have between a third and half of the values missing, and have a small number of values that were present but actually equal to 0. That's suspicious, and if we look at the data set, our suspicions will be raised further. So this is the data set itself. You can see that the first 2 columns are the property reference and the postal district, and then there are lots and lots of columns giving the monthly water readings all the way through over roughly a 5-year period. And what we can see when we're looking at this is some of the readings are missing. Most of the readings are floating point numbers, but some of those readings that do have a value are just the number 0. And it's this number 0 which is very suspicious. It seems highly probable that these are cases where a reading was not received rather than the reading was actually 0. So to summarize this step, what have we learned? We've learned that good datasets document each special value, and if you have documentation, then you should start by treating that documentation as a dataset itself and analyzing it. We've learned that it's dangerous to blindly use the defaults in software. You should always check them. And note that not all defaults are documented, and other defaults are case sensitive, even down to the individual letters. We've learned that one way to find special values is to check whether each numerical variable has the correct data type. If not, then the cause may be textual special values, or, as we saw in the example, you may have uncovered a bigger issue. For data that does have a numerical data type, then an approach is to create a box plot to visualize the outlying unique values, because those outliers often indicate special values, even though the approach isn't foolproof. And lastly, always be suspicious of data that has values of 0, especially if other values for that variable are decimal numbers. Once again, if you'd like to download the method, you can do so freely from this GitHub link. If you have any questions, then do feel free to contact me. Thank you.